This tutorial will cover the topics of elements, atoms, and atomic bonding as they apply to human anatomy and physiology. We'll begin with an overview of elements and the periodic table. We'll go on to talk about some features of atoms, and then identify how these atomic features allow for atomic bonding and the types of atomic bonding that can occur. So let's begin by looking at this periodic table that you see in front of you. This is a typical representation of a periodic table. You'll notice that although we have atomic symbols, we do not have the entire word or name of each element. This is typical of what you might find on your exam, where I'll give you the word or the name, and you'll need to be able to locate it on this periodic table. Now, which elements are fair game? Luckily for you, we're in a biology class, and there aren't actually that many elements that are found in large amounts in living organisms, and so we can limit our discussion of elements to the ones that we're likely to see inside of living systems. So I'm going to give you the top 10 elements that are found in the human body, and these are the top 10 that will be fair game on an exam. And I'm going to put a little mark next to each one as I identify it so that you can find it and follow along with me. So the most common element in the human body is oxygen, right here. And then we'll find a significant amount of carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, and chlorine. Now we can identify some of the key features about each element by using this periodic table to show us some information. So let's go ahead and we're going to use carbon here as an example. So we're working with carbon right here, and you can see on the periodic table that above the letter C, the atomic symbol for carbon, we've got a number 6. That 6 right there indicates the atomic number of carbon. And the atomic number of carbon, which is 6, is telling us how many protons are in the nucleus. This is a fixed number, it can't change. If I tell you I've got some carbon atoms, you can tell me there must be 6 protons in the nucleus. Another way to think of it is this isn't a variable number for any particular element. If I say I've got 8 protons in the nucleus of an atom, then you can tell me that we've definitely got an oxygen atom. Okay, and just as an aside, not something that we will really go into in this course, the number under the atomic symbol, you can see here for carbon is 12.011, is called the atomic weight, and that's telling us the average weight of carbon atoms, and the weight is both the protons and the neutrons that are found in the nucleus. So let's move forward and refresh what we've already learned in previous chemistry classes about components of a particular atom. We want to learn about these components because they're going to help us understand why atomic bonding happens and how it happens. So let's go ahead and use that carbon atom that we looked at a moment ago as our example for drawing out an atom. So the carbon's atomic number is 6, and so if I draw a carbon nucleus, then inside the carbon nucleus I can load in 6 protons, and I'm going to use a plus sign to indicate protons, since protons have a positive charge. Also, you remember that inside that nucleus you've got neutrons as well, and we're going to go ahead and assume that we've got an equal number of neutrons to protons, and so here we have a nucleus that's got 6 protons and 6 neutrons in it. Now we need to deal with the electrons. The electrons are orbiting around the outside of the nucleus, so they're out here, but they can't all be in the same space at once, and so we need to describe the fact that the electrons tend to orbit around the nucleus in shells, electron shells. And so we're going to draw some shells out here to indicate how many electrons and where they are. And then we'll also in a moment discuss the terms of valence shell and the octet rule that goes with it. So let's go ahead and draw our first electron shell, and I'm going to just use some dashed lines to indicate it. And this first electron shell, quite close to the nucleus, only has a maximum capacity for 2 electrons. So I'm going to use these open circles to indicate our maximum capacity for electrons, even though I haven't loaded any in yet. And then our next electron shell, further out, has a max capacity for 8 electrons. So I'm going to make 8 little spaces, 1, 2, 3, 4, 5, 6, 7, 8. Now let's talk about this electron shell right here. I could draw another one further out that also had a capacity of 8, and another one further out that also had a max capacity of 8. And so that's where we get this term octet rule. The word octet rule is describing the fact that the max capacity of your shells is 8. Obviously, the first electron shell sort of breaks that rule, and we just have to remember its max capacity is 2. But after that, max capacity 8, 8, 8, 8 if we keep going. And so we use that term octet rule to describe the maximum capacity of 8. And we're also going to describe in a minute with the octet rule the idea that this outermost shell is always going to be seeking to be complete. And that complete is, of course, again, full to 8. So the octet rule comes in there as well. So I'm going to grab a different color for my electrons so that we can write them in here. We had 6 protons and 6 neutrons, and so we're going to start out with 6 electrons as our typical amount. So I'm going to load 2 into the first shell, and then that means I can load another 4, if I've done my math right, into that outer shell. So I've got a carbon atom represented here. This outermost shell, again we use the term valence shell to describe the outermost shell, is not full. So we have not satisfied the octet rule. So something's going to have to happen with this carbon atom, and that's where we're going to move forward into atomic bonding in just a moment. So before we move forward, let's just quickly review what we know. We've got 10 elements on the periodic table that we're going to be responsible for in this class, and we should be able to recognize and use the atomic symbol to represent each of those elements, and we should also be able to identify what the number above the atomic symbol means. That is the atomic number, and it refers to the number of protons that are in the nucleus of atoms of that element. Inside the nucleus we've got the protons and the neutrons, and the electrons are orbiting around the outside in electron shells. The first shell has a max capacity of 2, and all subsequent shells, for our purposes, have a max capacity of 8. That octet rule describes those max capacities of each shell. And the octet rule also describes the fact that our valence shell, our outermost shell, is going to be seeking to fill all of the available spots. And so carbon's got a problem at this moment in this image because those available spots aren't full. The octet rule has not been satisfied. All right, let's move on to a fresh page and describe atomic bonding. All right, here we are. I'm going to talk about atomic bonding. And we're going to start with a relatively simple example of atomic bonding by using hydrogen, a relatively simple atom. So if you review the periodic table, you'll notice that hydrogen has an atomic number of 1, which tells us we've got 1 proton in the nucleus. Interestingly, hydrogen doesn't usually have a neutron in the nucleus, so a proton is all that's there. So let's go ahead and draw that first electron shell outside of my hydrogen, and we remember that the electron shell has a max capacity for 2. I know this is weird how I'm drawing my capacity, but it's going to help me in a minute. Max capacity for 2, but we've got 1 proton, which means we load 1 electron in. And here we are with hydrogen, and hydrogen has an octet rule problem. Our outer valence shell is not full. And so hydrogen is going to seek to satisfy that outer shell. And although hydrogen can do multiple things, one possibility for that hydrogen is that it will satisfy the outer shell by sharing its electron with another hydrogen. So here's a hydrogen nucleus, and I'm going to draw my electron shell overlapping, and when that new hydrogen brings its electron to the party, you can see now that something interesting has happened. Each hydrogen atom only had 1 electron, but now that they're sharing them, you can see that the valence shell of that hydrogen has 2, and the valence shell of this hydrogen has 2. This situation in which 2 atoms share a pair of electrons is called a covalent bond. So, covalent bond, definition is 2 atoms sharing electrons. This is a nice shorthand for electrons. Now, covalent bonds come in two flavors, if you will. So some covalent bonds, like the one I just shown you, is called a nonpolar covalent bond. And nonpolar covalent bonds exist when the two electrons are shared equally. And I'll explain what that means after I write it down here. Okay, what does that mean? You can see here that these two electrons are spinning around the outside of both this nucleus and this nucleus. Now, where those electrons will choose to hang out depends upon how much pull the nucleus has to the electrons, how much of an attraction it has. And because we've got two of the same type of atom, two hydrogen atoms, each nucleus has the same amount of power or pull over those electrons, and so the electrons are just as likely to be over here as they are over here, and our two electrons, each with a negative charge, absolutely balance out the two protons with each of their positive charges. And we end up with a non-polar. Electrons being shared equally, they're going to be found anywhere around the outside of these two nuclei in sort of equal amounts. Our other option for a covalent bond is something called a nonpolar covalent bond. So this is a second type of covalent bond. I'll write that in here. Or sorry, I did say nonpolar, polar covalent bond. And as you might have surmised, it's the opposite of a nonpolar covalent bond. Our two electrons that are being shared are shared unequally. Let me show you an example of this. I'm going to go ahead and draw you a water molecule, which is a great example of a polar covalent bond. Water is H2O, right? You've known that since probably about first grade. So I'm going to draw an oxygen atom and then use our valence shells to show you how the hydrogen atoms are bonded to it. So our oxygen atom, we're going to start with a nucleus, and that oxygen atom has 8 protons and 8 neutrons. Here's our first electron shell. I can load a maximum amount of electrons in there, 2. I've still got plenty to go since I have 8 total. And then I make my next electron shell, my valence shell. 1, 2, 3, 4, 5, 6, 7, 8. But because I have 8 protons, I only have 8 total electrons to load in. So if you count these green dots, you should count up 8. 2 went into the first shell, and then there were 6 to load into the valence shell, which leaves us with 2 empty spots in the valence shell. And the Octet Rule says that can't exist that way. Oxygen is going to tend to usually form covalent bonds to satisfy these last 2. And one of the possible things it can form covalent bonds with is hydrogen. So let's make a hydrogen nucleus with its 1 proton, and that shell, that valence shell, hydrogen brings an electron to the party, and we've begun to fill in oxygen's valence shell. So now we draw our other hydrogen shell and the other electron that the hydrogen brings to the party, and now here we are. We've satisfied everybody's Octet Rule. Each hydrogen has 2 electrons orbiting it, and each oxygen has a total of 8 electrons in its valence shell, and the Octet Rule is satisfied. Okay, so this looks a lot like the situation I drew up here, but something has changed. And the thing that's changed is the power of the nuclei. For the purposes of this class, I'll tell you and point out to you which atoms have very strong nuclei, very electronegative nuclei, and which atoms have weak ones. I'm going to write you a little rule off to the corner that you can use as a little hint to yourself, and I think of it as the Octet Rule. It's a little bit silly. This is an order of electronegativity. Oxygen is highly electronegative, nitrogen less so, carbon less so, and hydrogen less so. These two are almost equal to each other though, so we can think of those as having a shared low electronegativity, and there's our scale. High electronegativity, medium, and low ONCH. So this is an oxygen, these are hydrogens, and you can see that oxygen and hydrogen are the opposite ends of my electronegativity scale. So oxygen is going to have a very strong attraction of all 10 of these available electrons. Each of these hydrogens, a really poor pull on any of the 10. That results in some charges sort of shining through. So over here on this hydrogen end, I'm going to make this funny little symbol which means partial. I'm going to have a partial positive charge by each of my hydrogens. Why positive? Because I've got a positively charged proton and I don't have any electrons hanging around here sort of neutralizing that charge because they're all getting sucked over here to the oxygen end. And that means that the oxygen end of my molecule is going to have a partial negative charge. Again, why? I had 8 protons in the nucleus of my oxygen, but now there's 10 electrons hovering over on this side, creating a bit of a negative charge over here. That is a polar covalent bond. 2 electrons are shared unequally. Water's a good example, and let's write one more note in here. The result is a molecule that with charged, I'm going to say surfaces or areas. Regions where I've got partial positive charges where we couldn't hang on to the electrons, and regions where I've got partial negative charges where the electrons are hanging out more. Alright, so we've covered 2 of our 4 types of atomic bonds. We've covered nonpolar covalent bonds, and we've covered polar covalent bonds. So we've got 2 more types of, I'm going to underline those for you to make that clear, nonpolar and polar covalent bonds. I've got 2 more bond types to describe briefly. I've got ionic bonds to tell you about, and then we'll finish up with hydrogen bonds. Let's get that clear there for you. Okay, so what's an ionic bond? An ionic bond occurs when instead of having atoms share electrons, we have atoms that have either gained or lost electrons and are now attracted to each other by the differences in charges. So let's get that jotted down here for you. Atoms gain or lose electrons to become ions. Sort of step 1, and then step 2 is ions of opposite charges attract. Let me show you what I mean. So if you take a look back at that periodic table, sodium has a total of 11 protons. How did I know? I just looked at the periodic table. But sodium almost always loses one of its electrons, and so instead of having 11 electrons, it has 10. So what's going to happen to the charge of this sodium atom? Well, I've got 11 protons and 10 electrons, which means my sodium ion is going to end up with a single positive charge associated with it. In contrast, a chlorine atom, if you look at the periodic table, has 17 protons and likely gains an electron to have 18 electrons. So what kind of a charge is chlorine going to have? A single negative charge, and this is a chlorine ion. So when you use the word ion, we described an atom that has gained or lost an electron, and then ions of opposite charge, like these 2 guys here, will be attracted to each other and form an ionic bond. One final note that's quite important for ionic bonds in a biology class. Ionic bonds are incredibly weak in water. Why? Well, remember, water also has charges associated with it, right? And so these charges will get in between the attraction of these 2 ions for each other and separate these out. That's hugely relevant for an anatomy and physiology class because it means that we'll never see ionic bonds inside of a body. What will we see? Ions that are separate in our body. All right, our final kind of bond that we'll talk about, and we're just going to load that over here on the bottom here. They're called hydrogen bonds. Underline that with red to kind of help you keep track of what's happening here. Hydrogen bonds, I'm going to give you a definition first, and then I'll show you on this water molecule we've already got drawn in here. Hydrogen bonds occur when a hydrogen atom already in a polar covalent bond is attracted to something negative nearby. Why would that be true? Well, let's walk through this definition here. So a hydrogen already in a polar covalent bond. Well, we can see a hydrogen already in a polar covalent bond here. And if you remember, what did I tell you about hydrogen's nucleus? It's very low on the electronegativity scale. It's not good at holding on to its electrons, and so it very often has the partial positive charge on its side of the molecule. So we can assume that a hydrogen already in a polar covalent bond is often slightly positively charged. Let's sort of write that in. Equals partial positive charge. Let's look at the second half of this definition, is attracted to something negative nearby. Well, why would it be attracted to something negative nearby? Because it has a partial positive charge. Those opposite charges attract rule is going to apply, and anything negative nearby will be attracted to it. So the negative charge of a nearby water molecule will be attracted to this end of this water molecule. Or something else that has a negative charge, like say a chlorine ion, will be attracted to this end of a water molecule. So hydrogen bonds occur between a hydrogen that's already in a polar covalent bond and something else that's negatively charged nearby. I like to think of it as this. Hydrogen bonds don't happen inside to form the center of a molecule. They happen between portions of molecules and other things that are negative nearby. All right, a quick review before we wrap this up. We talked about 4 kinds of possible atomic bonding. Non-polar covalent bonds when 2 electrons are shared equally. Oh, let's add some examples in here of that. Molecular hydrogen is an example of a non-polar covalent bond. Molecular oxygen, molecular nitrogen. These are all great examples of non-polar covalent bonds. These ones are easy because you can see it's 2 atoms of the same kind. Obviously, they're going to share their electrons equally. Okay, and then we have polar covalent bonds. 2 electrons are still shared, but now they're unequally shared because the electronegativity of the atoms involved in the bond are different from each other. That gives us a molecule with charged surfaces. Third kind of bond, ionic bonds, occur when atoms gain or lose electrons to become ions, and then those ions attract opposite charges with each other. And then finally, hydrogen bonds happen between a hydrogen that's already in a covalent bond, and that's going to be attracted to something negative nearby.